has agents within it. So each agent within this model, it progresses through a series of health states, a progressing degree of severity. And within each health state, they exert a cost per year, and they exhibit a certain quality of life. There are, moreover, certain discrete transitions, such as occurrence of a transplant, by which, in this case, a kidney transplant, by which there's also accumulation of cost, and which have significant impacts on quality of life. So, for example, here there's an increase of $75,000 in terms of the accumulated costs when that kidney transplant occurs. Here we have individuals progressing. They have state-based costs as well as incidence-based costs, and there's some death associated with the whole scenario. Now, at the aggregate level, we're going to have use of stocks and flows, but in this case, those stocks and flows will be aggregate. They'll be totaling up the costs and quality adjusted life years lived and life years lived associated with different individuals in the population. And we include both discounted factors and undiscounted factors. So, for example, discounted health services cost, undiscounted, etc. So here we have this low-level population implemented in an aggregate fashion, and then we have a higher-level summary statistics, which are implemented as stocks and flows. A notable feature of this is that when that transplant occurs, we'll go back and look at that now that you've seen this basic model. When this transplant occurs, so when there's a transplant, one of the very nice features of any logic is, even though at a high level the dynamics are given by stocks and flows, we can actually directly increment. This is actually a stock at the high level, accumulated discounted costs, and we can simply say that plus equals $75,000. In other words, this equals this plus $75,000. And it will actually change that stock, update that stock for that, in that instantaneous fashion, conceptually instantaneous for that transplant-related cost. And here we take into account a discount factor. So here, ladies and gentlemen, we have, by and large, at the level of the higher level model, we have dynamics being described by stocks and flows, but when you do have special events that need to modify these in some operative fashion, you can do so by directly incrementing these values. Otherwise, where do these values come from? From whence do they come? Let us investigate. So let's go look at Maine. And let's go take a look at these inflows here. Alas. Okay. We're going to look at those inflows, and those inflows conceptually depend on so the rate of flow in to cost, for example, depends on the number of people out there and their health state. For each person, to sum up over all people in the population of their current health state times the cost per unit time. In this case, it's year, I believe, of associated with being in that cost state. So that's how those flows are generated. So let's go back to that, right? Here we go, and let's go to the costs here. Let's for example see this one, the undiscounted quantities. There's a number of new costs per year. Does anyone recognize what that probably is? If you say population.new cost per year, what would that be? It is a statistic. Thank you, Kurt. It is a statistic, so let's go down and look here. Population new cost per year. And what is that? New cost per year. It's just a sum up of cost per year for the person, actually, and cost per year, this item is the particular person. And if we go look at where their costs per year are dictated, we're going to see it's arguable whether this is the best way to do it. This is a variable here, and when they enter into, for example, this state, the cost per year is set to reflect that state. So, in other words, it's totaling up to find the rate of inflow in terms of cost per year coming into that stock. It's just totaling these things up to the population. As you can imagine, quality adjusted life years, it's also totaling up the quality of life for all these people in the population. So this is a model where we're using, again, a hybrid approach, and the hybrid approaches are delineated by the levels of structure once again, but rather than having agent-based level at the higher level and then system dynamics subservient to it, we instead have at the aggregate level we have system dynamics, and then we have agents circulating according to an classic agent-based description with state charts, and exerting these costs, which are then summarized at this very, very high level. Does that make sense? Okay. Finally, I would like to leave you today with another